Yes, a good morning to you, my dear students and all the people watching this program. Teacher Kakuri is in the house and I want to welcome you this morning to our usual lesson of applied maths. Before we go for the lesson, I want to remind the learners that we are still doing friction and this is going to be our third lesson. But I want to remind you that if you keep reading, usually as students, you keep leading, and winners do not quit. Otherwise, the quitters can never win. So as we prepare to start our lesson this morning, I want to encourage you to keep reading if you want to keep leading. And also to note that winners do not quit, and quitters can never win. And we were looking at friction. Last time we did several numbers, and we are left with one number which I'm going to start with in our discussion today. And right away, I will request my producer to show us the numbers. Remember, you need either to take a picture because you cannot copy the numbers as fast as the time available is. We are going to start by working through number 1, and we shall follow the order until when our lesson ends. Whatever will not be covered here will be taken as homework because we already have enough information to try them out. Number 1, as you can see it, we have a carton of mass, 3 kilograms, resting on a rough plane inclined at 30 degrees. So we sketch a diagram. The carton has a mass of 3 kilograms. If we let this be our mass, it means it exerts a weight of 3 g in newtons. It is inclined at 30 degrees to the horizontal, and they are telling us that the coefficient of friction between the carton and the plane is a third. They are giving us the value of mu as 1/3. We begin by indicating the forces acting. By indicating the forces acting, we shall have the normal reaction. Normal reaction, we shall let it be R. This acts perpendicular. That's why it is called normal, perpendicular to the plane. If we extrapolate this normal reaction, it gives us another force. Remember the angle geometry, this is 90, that would be 60, of 3g, the cos of 30 degrees over here. And we have another component here of 3g, the sine of 30 degrees. And they are asking us to find the horizontal force that should be applied to make the carton just about to move up the plane. Now, if we let the horizontal force act here, that horizontal force is going to act at the same angle. The reasoning here I want to emphasize, I will let this force be F. This, from your primary angle geometry, if this is the plane, for those who may not be aware, and this is the angle of inclination of 30 degrees, these two angles are alternate if this is my F. And therefore, this is also 30 degrees. So this angle will be 30 degrees. And you can choose actually to let this F pass through and indicate it here instead of there. Still, that would be 30 degrees. And this F therefore can be resolved for purposes of emphasis. It can be resolved along here where the 3 mg cos theta is, and it can be resolved along the plane as we shall see, or as we have been seeing. We'll complete that to indicate the components of F when we resolve. Now, since there is friction and this particle is being pushed, they're saying the force applied to make the carton just about to move up. If it is going to move up, it implies that the frictional force is going to act down. The frictional force is going to act down. So after illustrating all these forces acting, we can now do the resolving. Remember, I have said that F is going to have a component down here, which actually is supposed to be F, the sine of theta, of 30. And it will have a component up there, which is supposed to be F, the cos of the angle of 30 degrees. So after indicating all these forces, we resolve. If we resolve normal to the plane, normal to the plane is along the reaction line. We will have R, which is going up, being equal to 3g, the cos of 30 degrees, plus, when we resolve F along normal to the plane, the perpendicular will be here. So we will have F, the sine of 30, adding itself on that. We have assumed that F is the horizontal force, which we are looking for. We are assuming that F is the horizontal force which we are looking for. So we obtain this expression. I can substitute in for the values and say this is 3g root 3 over 2 plus F out of 2, and we label it as equation A. The next resolving is going to be along the plane. If we resolve along the plane, resolving along the plane, I expect students that have been following these lessons now to actually be resolving ahead of me so that they can confirm the answers. Along the plane, it means we are moving parallel to the plane. You can use parallel or along. It means we shall have this component of F going up. We shall have F, the cos of 30 degrees, this one which will be going up. In equilibrium, it should be equal to the frictional force, which I've called R, plus the downward component, which is 3g, the sine of 30 degrees. But remember, we know that Fr is the frictional force, which is equal to the coefficient of friction times the normal reaction. So if I substitute in again, I have F times the root 3 over 2 being equal to mu, and we know the value of mu, which is a third times R plus 3g times a half. So we can label this equation by saying that F root 3 over 2, F root 3 over 2 is equal to a third R plus 3g over 2. We can label it at this stage since it is the same and the space under here is not enough. So we are interested in finding the value of F That means we can substitute for R in equation B using equation 1. If we substitute for R, in B using A, will give us that f root 3 over 2 is equal to a third into R. But my R is 3g root 3 over 2 plus f over 2, then plus 3g over 2. We are looking for f. Now we do the mathematics. Yeah. So our f root 3 over 2 is going to be equal to g over 2 root 3. This 3 will cancel, plus f over 6 plus 3g over 2. So we correct like terms for f. We shall have our f into root 3 over 2 minus 1 out of 6 should be equal to g over 2, which is common, into root 3 plus 3. If we take the LCM, we can have our f, the LCM as 6, will give us 3 root 3 minus 1 being equal to g out of 2 into 3 plus root 3. If we make f the subject, this 6 will simplify with that 2 to give us a 3, g into 3 plus root 3 all over 3 root 3 minus 1. If we substitute, we shall have 3 times 9.8 into 3 plus approximately the root of 3 is around 1.732 over 3 times 1.732 minus 1. If we compute to find the value of f using your calculators, if you compute that, you should be able to get the answer. You should be able to get the answer approximately as 33.15. They did not specify the number of decimal places. We can approximate it to 33.15 newtons to 2 decimal places. The accuracy, the degree of accuracy is 2 dPs. There are several ways you can draw this sketch diagram. There are several ways which we may not have to go into. One of them is this one. If I chose not to indicate this, I can leave it as that, where the particle is here, and put all the other forces as indicated in the first diagram to act on that diagram. You can capture that solution as we prepare to go for the next number. Remember, whenever they say the particle is being pushed up, friction must act in the opposite direction. And if they say the particle is sliding down, it means friction is acting in the opposite direction, as per the definition we agreed on at the very start of this topic. A few minutes for you to capture that, and we progress to our next number. and we progress to our next number. We can move to our second number. We'll request the producer to forecast the second number. The second number is over there. And I will, as usual, request that you can take a picture of that number so that you can fill up that question in your notebook later. We shall move to interpret that number. A body of mass m is just prevented from sliding down. If this body is prevented from sliding down, it means that the frictional force is going to be acting in the opposite direction. So, if they are telling us that the coefficient of friction between the body and the plane is mu, and they are asking us to prove that the angle of inclination of the plane to the horizontal is, I will make a correction there. That should just be the arctan. That tan should be removed for those who are following. So we want to show that the angle is actually the arctan. The arctan. So if we let that angle be theta, let theta be the angle we are looking for, the angle to the horizontal. We will make our sketch and let this be the theta which we are looking for, or which we need to show that is equal to that. After that, we are going to attach our particle. If this is our particle, they are telling us this particle has a mass of m kilograms, so it will exert a weight, which will be m times g. Weight is given by that. Definitely, it will have a downward component, which is supposed to be mg, the sign of the angle we are looking for, theta. It will have a normal reaction, which we shall call r. And since it is prevented from sliding down, I told you the frictional force will act up. This frictional force is mu times the normal reaction. And when we extrapolate this, we have another force here, which is the weight times the cosine of this angle theta here. The geometry of angles, by now we have enough experience about it. And they are telling us a horizontal force of mg over 2. This force that we were looking for here this time round is given as a half of mg. The horizontal force is given as a half of mg to keep this particle from sliding down. And the coefficient of friction is given as mu. They are asking us to find the value of theta. Find the value of theta. So we shall still resolve. That's why I said that these things are supposed to be easy. This force could be taken to go through as per the previous example. And we are going to resolve both normally, that is, and along the plane. Resolving normal to the plane means that r will be equivalent to mg, the cosine of theta plus now m out of 2g, the sine of theta. If we resolve this, the 90 is here. So we are looking for the component here which will be going down. And without wasting any time, we can call this equation A. And straight away, we resolve along the plane, along or parallel to the plane. If we resolve parallel to the plane, mg out of 2 times the cos of theta will be acting in the same direction as the frictional force, and in equilibrium, they will be equivalent to the downward component, which is mg, the sine of theta. If I substitute for the frictional force, which we know is mu r, we shall get that mg over 2, the cos of theta, plus mu times r should be equal to mg, the sine of theta. And we shall call this equation B. Since our interest is to find theta, we are going to substitute. We are going to make a substitution of r into equation B. It's exactly the same as the previous number, only that now we are trying to derive an expression. So substituting for r in B, using A, we shall have mg out of 2, the cosine of theta, plus mu into mg, the cosine of theta, plus mg over 2, the sine of theta, being equal to mg, the sine of theta. The rest is now trying to open brackets and rearrange here and there. If we open brackets, we shall have mg over 2 cos theta plus mu mg cos theta plus mu mg over 2 sine theta should be equal to mg sine of theta. As you notice, each term here has mg, so the mg will cancel out. The mg will cancel out. I am going to eliminate it in our next working and correct like terms. I am going to eliminate it and correct like terms at the same time. Cos with cos, I will have a half the cosine of theta into a half plus mu will be equal to the sine of theta into 1 minus mu half, mu over 2. If I take the LCM, I will have 1 plus 2 mu over 2 into the cos of theta should be equal to 2 minus mu over 2 into the sine of theta. Since I am interested in getting the tan of theta, I will divide by cosine, divide by. This 2 will cancel, divide by cos theta into, I'll divide by cos theta into this. If I divide by cos theta throughout, I will get that 1 plus 2 mu should be equal to 2 minus mu into the tan of theta. The division has been done direct, implying that my tan of theta, if I make it the subject, would be 1 plus 2 mu out of 2 minus mu. And therefore, this implies that theta will be the tan inverse of 1 plus 2 mu out of 2 minus mu as required to be shown. So systematically, once you follow the steps, you should be able to get what is required. Of course, the most important thing to the student following this lesson is consistency in solving the equation. I have divided by theta. I have not included that step, but it is clear that if you divide cos theta here and cos theta here, this one will cancel. These two cancels out. Someone may say, where did that two disappear? From experience, I know that, but there was that too. They cannot actually see that it cancels out. And that is sometimes normal, but of course not right for a student to fail to see that. This number has a part B, which we shall shortly be going for. We can again allocate a few minutes for you to capture this, and then we go to part B. We are allocating a few minutes for you to capture this. Remember, if you are not as fast as me, you may not deceive yourself that you'll copy this. If a few students can actually copy this within the time limit given. So the fastest way is you can take a picture and catch up later. As long as you have followed the teacher as they go through, you can always catch up with the copying at a later time. We go to part B. And part B says that they have given us the value of mu. They have given us the value of mu as a half. And they want us to show that the magnitude of the least force, this time parallel to the plane, that will just move the body up, is given by that value. So part B has a slightly different sketch. And before we get that least force, we must get the value of theta. We must get the value of theta here. So in part B, they have given us mu. If mu is a half, it implies from the expression we have just obtained, we can get theta. If mu is a half, from the expression of tan theta being equal to 1 plus 2 mu out of 2 minus mu, we can say that our tan of theta is 1 plus 2 times a half over 2 minus a half. And if we simplify this, we have 2 over 4 minus 1, which is 3 out of 2. So the tan of theta is actually 4 out of 3 if we do the mathematics, which implies that theta is actually the tan inverse of 4 out of 3. Now, since they want us to show that the minimum force, to show the minimum force, we need the minimum force they want is the force that will be required to ensure that this particle, they are saying find the minimum force required show that the magnitude of the least force parallel to the plane that will just move the body up is that. If we let the force we want, which is parallel, be here, I'm going to call it P. It should be a minimum force. Downwards, we have a component of force that must be dotted, and this is mg, the sine of the angle. Remember, we now know what theta is. Vertically or normally, we have the reaction, and we also have this force, which is mg, the cos of theta, and the normal reaction, which is 3g. The mass is m. So they want us to show that the value of P is given by, or is equivalent to that value we have. From here, if I may quickly find from theta, tan theta is opposite of adjacent. It implies by Pythagoras theorem that this would be 5. And therefore, it implies that the sine of theta is 4/5, and the cos of theta is going to be 3/5, where we need them. So resolving, we again resolve normally. Resolving normal to the plane. Normal to the plane will give us in equilibrium that R is equal to mg, the cosine of theta. I can call this 1. And resolving along the plane or parallel to the plane, parallel to the plane, can also still give us that the minimum force P, remember there is friction here, which I had forgotten. Since this minimum force is required to move it up, the friction force will act down. So P minimum, which we are looking for, will be equal to mg, the sine of theta, plus the frictional force, which is mu times r. So we will solve these two expressions to look for the value of P minimum. We are repeating the same concept, but using different numbers. Different numbers. So it is only the values that are varying. That's why I want to assume that learners following this lesson should be able, they should be able to do the questions that will be left behind successfully. So we shall substitute for R, and that means our P minimum will be mg, the sine of theta, plus mu into R. My R is mg cos theta. So plus mu mg, the cos of theta. Since we have the value of mu, I think mu was given. We are going to substitute in for mu, and we substitute in for the sine and cos. We have our sine of theta as 4/5. We have our cos of theta as 3/5. And we have our mu as a half. So the minimum force, which actually we are supposed to show, will be mg times 4/5 plus a half times mg times 3/5. If we do the mathematics, our mg is constant, so we can pull it out. And 5. Can pull out mg out of 5. We stay with 4 plus 3 out of 2. When we take the LCM in there, we shall have our P minimum giving us mg out of 5 into the LCM will be 2. We shall have 4 times 2 plus 3. If we work out this, we have mg out of 5 times 11 out of 2. And therefore, finally, we can confirm that the minimum force required will be actually 11 mg out of 10 newtons as required, because they wanted us to show that the minimum force will be given by that value. So the minimum force will be given by this expression as was required. The beauty with mechanics, numbers from my experience as a senior educationist is that the student actually leaves the lesson when they actually know they have got the thing right. They leave the lesson or the examination room when they know they have got the thing right. As you capture that solution, we warm up yet for another number, which we shall be looking at shortly. We warm up yet for another number, which we shall be looking up at shortly. As you capture that, allow me to remind you that the greatest gift that teachers give out exclusively is knowledge. That is the greatest gift. And it is important that I continue to applaud my colleagues out there that are touching the different lives of students in many ways, the most important being the academic and the psychological one. One other writer said, the teachers who love teaching teach children to love learning. Teachers who love teaching teach children to love learning. And like I told you, teaching is ideally a calling. Not much can be amassed in terms of property from the blackboard, but the lives you touch, the lives you change, the lives you transform. Because whatever you give in class, you have given someone permanently unless they choose to forget it. I want to request the producer to take us to the next number. And that is number 3. I expect that number 3 should be able to bring us to the end of our lesson today. But I want to applaud the junior teachers. They are teachers that I respect so much, and these are teachers that take over the job after the natural teachers who are parents. The teachers of kindergarten schools, wherever you are, kudos to you. These are guys, allow me to call you guys, these are guys that start with the children before they even learn how to write. And they bring these children into a state where they begin to write on their brain. Psychology tells us that we are born tabula rasa. Human beings are born with an empty brain, and as they grow, nature continues to write on their brain. Because there is a force that I need to show, this sketch should be giving me enough space up. So our number 3 is going to be, it may look scaring, but it is a brief number. It is a brief number. partly under motion, actually fully under motion, but with an element of friction. That's how it comes in here, with an element of friction. I know we looked at numbers similar to this sometime at the start of this program. So we are indicating, I'm beginning to indicate the forces acting. Since this is 2 kilograms, these are forces now. It is not grams, but they are forces. And we will have a normal reaction here and the weight at the same time. The weight is 5. The normal reaction, I will still call it R. They have given us acceleration. When we release this system, by default, the heavier particle will pull. So this will go up, this will follow suit, and that will follow suit. They have given us the acceleration as 0.28 meters per second squared, and it is the same all throughout. 0.28. A is 0.28. Now these are strings. There are 2 strings. We shall let the tension here be T1 and the tension in this other part of the string be T2. There are 2 strings and therefore they have different tensions. Since the system is moving in a clockwise, in an anti-clockwise direction, it means the frictional force is going to act here because the frictional force is on the table. So the frictional force, which I will still call Fr, is going to act there, and it will still be normal to the plane. So it is still equal to mu r. Now, they want us to find the coefficient of friction. They want us to find mu. Mu is not known. We shall use F is equal to ma here, our resultant force, and we shall categorize it in 3 forms. For the 3 kilogram mass, since it is going down, the resultant force will be 3g minus the tension there, T2, and this will be equal to 3 times the acceleration. I'll call this equation 1. For the 5 kilogram mass, which is on the table, the 5 kilogram mass is this one. It is acted on by the strings. Since it is going this side, the resultant force will be T2 minus T1 minus the frictional force, which I've called Fr, should be equal to 5a. But since we know that Fr is equal to mu r, and by the way, R is the weight in equilibrium. R is equal to 5g. So my T2 minus T1 minus mu times 5g would be equal to 5a, would be my second equation. For the 2 kilogram mass, it is going up. And remember, we know the value of A, so I will feed it in later. My T1 minus 2g should be equal to 2a. They are asking us to find the value of mu, but we shall eventually find the tensions or the forces as well. The easiest way to find mu, and this I am sharing for all the students following this. Whenever you have pulleys and connected particles, the easiest way to find acceleration, for example, if it is not given, is simply add the equations all at a go. Adding 1 plus 2 plus 3 at a go will eliminate all the forces acting and allow us to find the acceleration. But since we have the acceleration, we shall add, and I will not skip any step. So 3g minus T2, I am adding all the left-hand sides at a go, plus T2 minus T1 minus, I'll write this as 5 mu g plus T1 minus 2g will now be equal to 3a plus 5a plus 2a. Why I said all these forces will cancel, you notice this cancels, the additive inverses, and this cancels. So I have g from 3 and 2 minus 5 mu g being equal to 10a. But my a is known. But a is 0.28. So I'll feed in my a and look for mu. That's why I was telling you that this is a short number. So my a, my g into 1 minus 5 mu. Okay, I can say my 9.8, since g is known, minus 5 mu times 9.8 will be equal to 10 times 0.28. And I can say that 5 mu times 9.8, if I make it the subject, this 5 mu, if we make it the subject, will give us 5 mu will give us 9.8 minus 2.8. If I make it the subject by taking it there, I must subtract this there. So my 5 mu times 9.8 will actually give us 7. And therefore mu, which is the friction, will be 7 out of 5 times 9.8. If we do the simplification, 9 times 5 is 45, and 5 times 8 is 4. So we are getting 7 out of 49, which we can write as 1 out of 7. If you want, in decimal points, you can write it as 0.1429. 0.1429. So we can say that the value of the coefficient of friction, which we said is mu, is 1 out of 7. Now I said we need to find the tensions. To find the tensions, that is T1 and T2. Our T1 from equation 3 will be equal to 2 times 0.28 plus 2 times 9.8. Remember, in applied maths, G is 9.8. And when we compute that, we shall get the answer. And to find T2, we shall use the first equation. Our T2 also will be 3 times 9.8 minus 3 times 0.28. And if we compute this, we shall get our T1 as our T1 as 20.16. Our T2, when we compute, shall be 28.5 newtons. Otherwise, according to this question, we are mandated to solve up to here. But for purposes of further learning, I want to show the students attending this lesson that we can also find the values of T1 and T2 so that we completely solve that number. Yes, we are left with two numbers, And these two numbers are going to serve as an exercise. So capture this, and in a short while, I will be requesting that they show you the revision numbers. We shall be officially closing this topic today. That means that when we appear for our next lesson of mathematics, which will be a fortnight from today, we shall have to start another topic. With interest, given that we spent quite some good time doing statistics, I will take another short applied mechanics topic for our next lesson. Take a picture of this solution and capture questions 4 and 5 as self-test questions. Self-test simply because you are going to do them alone, and they are proof numbers. The answers, you can be sure that you have got the answers because the answers appear right over there. They appear right over there. Maybe some other information that I need to share on question number 4. On question number 4, allow me to inform all viewers following this lesson that the root 3 is not including the sign. Root 3, it is mg into the cos of lambda plus root 3 times the sine of lambda. The sine of lambda is not under the root, but the whole thing is over 2. Or it is mg over 2 into the bracketed term, but root 3 is independent of the sine of lambda. So they are proof numbers, exactly the same knowledge we have been using. You only need to take precautions to be steady and consistent. I want to thank you for attending this lesson, and I want to thank you for always following up my work on the social media, YouTube, and encourage you to continue following. I remain Teacher Kakuru, and I want to wish you a good day. God bless you.